Let's begin with a warning, not a dramatic one, just an honest one. If you're expecting a clean, final answer to the question, what is light really? You're going to be disappointed. Not because physicists don't know enough, and not because the universe is playing tricks on us, but because the question itself is shaped by how the human mind wants reality to behave. Nature does not promise us simple pictures. It only promises consistent outcomes. Most physics students believe they understand light. They've heard the standard explanation many times. Light behaves like a wave in some experiments and like a particle in others, so we say it is both a wave and a particle. The phrase sounds sophisticated. It sounds like a deep insight earned after centuries of scientific struggle. In practice, it often becomes a stopping point rather than a beginning. Once students memorize that sentence, they feel the problem is solved and they move on. But that sentence hides more than it reveals. A wave is something very specific. It spreads continuously through space. It interferes with itself. It does not arrive in isolated chunks. A particle is also something very specific. It is localized. It has a position. It goes from one place to another along a path. These ideas come from everyday experience. We invented them to describe water, sound, dust, stones, and bullets. They work beautifully in the world we evolved in. Light does not belong to that world. When we say light is both, we are quietly admitting that neither idea really works. Instead of confronting that failure directly, we glue the words together and call it understanding. But combining two wrong pictures does not produce a right one. It just produces a more complicated misunderstanding. The deeper problem is that we are asking the wrong kind of question. We keep asking what light is as if it must be a thing with familiar properties, like an object you could imagine holding in your hand. But light does not behave like anything you have ever touched, thrown, or watched move across a room. Every attempt to force it into those categories ends in contradiction. What physics actually discovered in the 20th century was not that light has a split personality, but that our classical concepts have limits. There are experiments where treating light like a wave gives perfect predictions, and others where treating it like a particle works exactly. But there is no single experiment where light behaves like a classical wave and a classical particle at the same time. The both only exists in our language, not in nature. This is where students often miss the most important lesson. Physics is not a collection of pictures. It is a collection of rules that tell us what outcomes to expect when we interact with the world. Light obeys those rules with astonishing precision. The confusion comes from our demand that those rules be translated into familiar images. The truth is uncomfortable but simple. Light is not misbehaving. It is not mysterious in the sense of being vague or sloppy. It is doing exactly what the equations say it will do. What fails is our instinct to reduce everything to common sense stories. The moment we accept that limitation, we stop treating wave or particle as an answer, and we begin to see it for what it really is, a signpost pointing toward the edge of human intuition. To understand why a light confuses us so deeply, we have to look at the tools our minds already had long before physics became a science. Humans did not evolve to understand atoms, fields, or quantum behavior. We evolved to survive at human scale. To do that, we built simple mental models of how the world works, and those models were shaped entirely by everyday experience. For most of human history, there were only two kinds of physical behavior that mattered. Some things moved as solid objects. Stones, arrows, animals, and later bullets all shared the same basic idea. They were localized, they followed paths, and at any moment they were either here or there. These were the things we now call particles, though no one used that word at the time. The idea of a particle was never invented by philosophers. It was invented by hunters. Other things behaved very differently. Sound spread through air. Ripples moved across water. Vibrations traveled along ropes. These things did not stay in one place, and they did not move as solid objects. They spread out, overlapped, and interfered with each other. These were waves. The concept of a wave was invented by musicians, sailors, and anyone who had ever watched water move. These two ideas worked extraordinarily well. By the time science matured, they had become so successful that we assumed they must describe everything. When Newton described light, he tried to fit it into the particle picture. When others studied reflection and refraction, waves seemed to explain more. The debate lasted for centuries, not because light was being difficult, but because our imagination had only two boxes to offer. The crucial mistake was never choosing the wrong box. The mistake was assuming there must be a box at all. Waves and particles are not fundamental truths about nature. They are models, approximations that summarize patterns we observe at human scale. They are shortcuts our brains use to compress experience into something manageable. As long as we stay in the world of everyday objects, these shortcuts work so well that we forget they are shortcuts. When light entered the picture, the shortcuts broke down. Light sometimes left marks on photographic plates as if it arrived in tiny packets. At other times it spread out and interfered with itself like a wave on water. Instead of questioning the models, we question the light. We ask, which one is it? When we should have asked, why do our models fail here? This is why the language of physics becomes dangerous when it sounds too familiar. Words like wave and particle carry hidden assumptions. They smuggle in images from daily life that simply do not apply. Once those images take hold, students begin trying to imagine how light switches between roles or how it can secretly be both at once. That struggle is not a sign of deep physics. It is a sign that the imagination is being asked to do a job it was never designed for. What actually happened historically is much simpler and much more unsettling. Physicists discovered regularities in how light interacts with matter. They wrote equations that predicted those regularities with astonishing accuracy. Only afterward did they argue about how to talk about them. The pictures came last, not first. The human brain desperately wants a story with objects moving through space and time. But nature does not owe us that story. The ideas of wave and particle are not wrong. They are incomplete. They describe fragments of behavior under specific conditions. Light itself is not obligated to resemble either one. It simply follows rules that lie deeper than the images we inherited from everyday life. Now we come to the experiment that forces us to stop pretending we understand what light is doing. It looks simple, almost childish, and that is part of why it is so dangerous to our intuition. You take a barrier with two narrow openings and place a screen behind it. When light passes through the openings and hits the screen, you do not see two bright regions as you would expect from tiny pellets flying through. Instead, you see a pattern of bright and dark bands spread across the screen. If you have ever seen ripples on water, this pattern feels familiar. Waves coming through two openings overlap, reinforce each other in some places, and cancel out in others. The result is an interference pattern. So far, nothing seems shocking. It is natural to say light must be a wave. The shock arrives when you slow everything down. You turn the source down until photons are sent one at a time. Not a weak beam, but individual, isolated events. Each photon hits the screen at a single point, like a tiny particle. There is no smearing, no half hit, no visible wave arriving, just a dot. But if you leave the experiment running long enough, those individual dots slowly build the same interference pattern. Bright and dark regions appear statistically, even though each photon arrived alone. There is no second photon to interfere with. There is no crowd effect. Each event looks particle-like, yet the overall pattern looks wave-like. This is the moment where language collapses. Asking which slit the photon went through sounds reasonable, but the experiment refuses to answer. If you try to measure the path, the interference pattern disappears. If you do not measure the path, the pattern returns. The behavior depends on how you interact with the system, not on some hidden classical story playing out in the background. The disturbing lesson is not that light is clever or mysterious. The lesson is that the idea of a definite path is something we brought with us, not something nature promised. The experiment does not show light switching identities. It shows that certain questions simply do not apply. Before detection, there is no fact of the matter about which slit the photon used. The pattern on the screen is real, repeatable, and precise. Our classical picture of what must have happened is what fails. At this point, many people try to rescue their intuition by asking what the photon is really doing when no one is looking. The question feels unavoidable. If a dot appears on the screen, surely the photon must have followed some path to get there. Surely it went through one slit or the other, even if we did not see it. This way of thinking is so natural that it feels almost irrational to doubt it. But the experiment keeps refusing that story. When we design an experiment that can determine which slit the photon passes through, the interference pattern vanishes. The result now matches what we expect from ordinary particles. When we remove that capability, the interference returns. Nothing else about the setup needs to change. The same light source, the same slits, the same screen. Only the kind of question we ask of the system is different. This tells us something deeply unsettling. The photon does not carry a hidden label saying which path it took. The path is not merely unknown, it is undefined. The idea of a definite trajectory only becomes meaningful when the experimental conditions demand it. Without that demand, the concept simply does not apply. This is where classical thinking quietly breaks. In everyday life, objects have properties whether or not we look at them. A stone on the ground has a position, even if no one measures it. We assume this because it has always worked for large objects. But light does not behave that way. Certain properties only come into existence during interaction. This does not mean consciousness creates reality or that observation is magical. The word observation is misleading. What matters is physical interaction. To detect which slit the photon uses, it must interact with something capable of recording that information. That interaction changes the situation. It is not revealing a pre-existing fact. It is creating a new one. The mistake is imagining a movie playing behind the scenes, with the photon following a secret path that we disturb by measuring it. The experiments do not require such a movie. They work perfectly without it. What exists before measurement is not a path or a position, but a set of possibilities. The moment an interaction occurs, one of those possibilities becomes actual. Our discomfort comes from wanting the story to exist before the fact. Nature simply does not provide it. Once this point is reached, many students try to soften the blow by saying the probabilities only reflect our ignorance. They imagine that the photon really does have a definite position and path, but we just do not know them. Probability, in this view, is a placeholder for missing information, like guessing which card was drawn from a shuffled deck. This way of thinking is comfortable because it preserves the idea that reality is fully defined at all times. But quantum experiments do not support that comfort. In classical situations, probability disappears when you gain more information. If you knew every detail of a thrown ball, you could predict exactly where it would land. In quantum physics, even when you know everything the theory allows you to know, probability remains. It is not a temporary flaw in knowledge. It is a permanent feature of how light behaves. The mathematical object used to describe light is called the wave function. Despite the name, it is not a physical wave sloshing through space. It does not carry energy or mass in the way water waves do. It is a tool for calculating probabilities of different outcomes when interactions occur. It tells us how likely a photon is to be detected at various places, not where it already is. This distinction is crucial. The wave function does not describe an uncertain reality hiding underneath. It describes a reality that is genuinely not settled until interaction takes place. When a photon is detected, the wave function changes abruptly, not because something moved faster than light, but because the situation has changed. A possibility has become an event. Attempts to imagine the photon as secretly well defined before detection lead to contradictions with experiment. If such hidden details existed and behaved classically, they would leave detectable traces in the statistics. They do not. The probabilities are not disguises. They are the best possible description nature allows. This is where many explanations quietly cheat by smuggling classical images back in. They talk as if the photon spreads out as a wave and then suddenly decides where to land. But decision implies intention and spreading implies substance. Neither idea is required. All that exists prior to detection is a structured set of probabilities governed by precise rules. The discomfort we feel here is not a sign of mystery in nature, but of a mismatch between how our minds want reality to behave and how experiments show it actually does. By this stage, a familiar phrase usually appears, offered as if it resolves everything: wave-particle duality. It sounds profound, almost poetic, and it gives the impression that light is cleverly switching between two identities depending on the situation. For many students, this phrase becomes a resting place, a way to stop asking uncomfortable questions. But wave-particle duality is not a deep explanation. It is a historical compromise. The phrase exists because early experiments forced physicists to use wave mathematics in some cases and particle language in others. Instead of inventing a new conceptual framework immediately, they reused old words and stitched them together. This was practical, not philosophical. It allowed calculations to move forward while understanding lagged behind. The danger comes when the phrase is taken literally. Light is not half a wave and half a particle, nor does it switch costumes when we are not looking. Waves and particles are classical ideas with precise meanings. Light fits neither one. When we say it is both, we are really admitting that our classical categories have failed. There is no experiment in which light behaves like a classical wave and a classical particle at the same time. In experiments where interference appears, there are no localized trajectories. In experiments where localized detection occurs, the wave picture no longer applies. The behavior is consistent, only our descriptions change. This is why the phrase can quietly block understanding. It suggests that the mystery lies in light, when the mystery actually lies in our language. We keep trying to force a quantum phenomenon into concepts designed for the macroscopic world. A better way to think is this: light is described by a quantum framework that does not resemble either classical picture. Wave and particle descriptions are approximations that emerge in certain limits, much like the idea of a rigid object emerges from the collective behavior of atoms. They are useful, but they are not fundamental. When students let go of the need to imagine light as something familiar, the confusion begins to fade. What remains is not a tidy picture, but a set of rules that work every time. That is not a failure of physics. It is a reminder that understanding does not always mean visualization. Another place where intuition quietly misleads us is in the way we think about measurement. In everyday life, measuring something feels passive. You look at a ruler to see its length, or you glance at a clock to read the time. The act of observing seems separate from the thing being observed. We carry this assumption into physics without noticing it. At the quantum level, that assumption fails. Detecting light is not like taking a photograph of a scene that already exists. To detect a photon, it must interact with matter. It must transfer energy to an atom, an electron, or a detector. That interaction is not a gentle peak. It is an event that changes the system. Without such an interaction, there is no detection, and without detection, there is no definite outcome. This matters because many properties we casually talk about, such as position or path, only become well defined during these interactions. Before detection, asking where the photon is located is not like asking where a hidden object sits in the dark. It is more like asking a question that has no answer yet. The concept itself depends on the measurement setup. This does not mean that measurement creates reality out of nothing. It means that reality at the quantum level is structured around interactions, not pre-existing attributes. The photon is not carrying a complete list of properties as it travels. Certain properties only emerge when the conditions demand them. The word observation often causes confusion here because it suggests a human mind watching. Human awareness is irrelevant. A detector left running in an empty laboratory produces the same results. What matters is physical interaction, not consciousness. Once this is understood, many paradoxes begin to dissolve. The photon does not change its behavior because we looked at it. It behaves according to the interactions we allow or prevent. Different experimental arrangements ask different physical questions, and nature responds consistently to each one. The discomfort comes from wanting measurement to be a neutral window onto reality. At the quantum level, there is no such window. There are only interactions, and those interactions define what can meaningfully be said about the system. Imagine living in a universe where letters only appear when you open your mailbox. Before the mailbox is opened, there is no letter inside. There is only a set of possibilities, a statistical prediction of what might appear. Asking whether the letter was really there before opening the mailbox is meaningless. The question does not apply to the system, because the system does not contain a definite outcome until the interaction occurs. Light behaves in a very similar way. A photon is not a tiny ball traveling along a path hidden from view. Before detection, it is not meaningful to assign it a definite position or trajectory. All that exists is a structure of probabilities defined by the experimental setup. The photon's behavior is not random chaos, nor is it secretly predetermined. It is constrained by strict rules that predict where and how it may interact, and nothing more. The double-slit experiment illustrates this clearly. When we do not measure which slit the photon passes through, an interference pattern emerges. When we do measure it, the pattern disappears. The photon does not decide or know what we are doing. Its behavior reflects the interaction conditions allowed by the setup. The moment a measurement occurs, one possibility becomes an actual event. Before that moment, the question of which slit simply has no answer. This way of thinking challenges every intuition we carry from daily life. In classical physics, objects exist in well-defined states independently of observation. In quantum physics, certain properties exist only when the conditions define them. Reality is not built from tiny, pre-existing objects with predetermined trajectories. It is built from potentialities, from structured possibilities that become definite only during interaction. Accepting this does not require mysticism, imagination, or belief. It is a conclusion drawn from experiments repeated thousands of times with results so precise that no classical hidden explanation fits. Light is not mysterious because it is clever. It is mysterious because it follows rules our brains did not evolve to understand. The universe is asking questions we never thought to ask, and in answering them, it refuses to fit our preconceptions. What we know about light is astonishingly precise, even if our intuition struggles to keep up. Experiments have repeatedly confirmed that light is quantized, arriving in discrete interactions called photons. These interactions are not vague. They occur in exact amounts of energy that can be measured to extraordinary precision. Light also exhibits interference patterns under conditions where many photons interact statistically, showing behaviors that seem wave-like. Both of these properties, particle-like quantization and wave-like interference, are observed consistently across countless experiments. We also know that light obeys the rules of quantum electrodynamics, the most precisely tested theory in the history of science. The predictions match experiments to many decimal places more accurately than almost any other physical law. This is not a matter of guesswork. It is exact, repeatable, and reliable. Every time we interact with light in a controlled way, the outcome aligns with these quantum rules. The patterns, the probabilities, the energies, they all follow a consistent mathematical order. Yet, for all this certainty, there are limits. We do not know what a photon is, in classical terms. We cannot picture it traveling along a path like a tiny particle, or spreading out like a water wave. The question itself is misleading because the assumptions behind it belong to a classical world. We also do not know what truly happens between measurements. The photon's wave function predicts the probabilities of outcomes, but whether it exists in some familiar sense before detection is not something the theory answers. We cannot observe it without interaction, and interaction itself changes the system. Humans struggle to grasp these ideas because our brains are designed for a world of objects and causes. We evolved to track stones, animals, and tools, not probability distributions and potentialities. Light does exactly what it is supposed to do, following precise mathematical rules. The mystery is not in nature's behavior, but in our expectation that it should behave like the familiar world we evolved to understand. Accepting this tension between precision and incomprehensibility is essential to truly understanding light. The aspects of light that remain unknown are as profound as the aspects we understand. We do not know what a photon really is, in the sense that we can imagine a familiar object. It does not have a trajectory or a defined position independent of measurement. We do not know what happens between interactions, what exists before a photon is detected, or whether space and time themselves are fundamental or emergent. Any attempt to describe these things using everyday intuition leads to contradictions with experiment. The universe simply does not conform to the categories our minds evolved to handle. We also do not know whether deeper layers of reality exist that could provide a classical-like explanation for quantum phenomena. Hidden variable theories have been proposed, but experiments such as Bell's test show that any such theory must violate local realism, something that feels impossible in everyday life. Nature allows no escape into the comforting classical world we imagine. It demands that we accept its rules on their own terms. The probabilities, the interactions, and the correlations are all that exist at the most fundamental level. Humans, because our thinking is hardwired for cause and effect, for objects moving along paths, for narratives with beginnings, middles, and ends. Quantum reality defies that structure. The rules of light and matter are consistent, exact, and universal, but they are not intuitive. They challenge our assumptions and force us to revise the way we think about existence itself. The philosophical but scientific conclusion is that reality is not made of things in the sense we usually imagine. It is made of events, interactions, and possibilities that only become definite under certain conditions. Light is not a particle, nor a wave, nor even both. It is a quantum phenomenon that reveals itself through interaction, governed by precise and unbreakable rules. Accepting this changes how we see the world. It teaches that the universe is less like a machine of pre-existing objects and more like a web of relationships and potentialities, where certainty arises only at the moments when we probe it. This understanding does not satisfy the need for a familiar picture, but it brings us closer to the true architecture of reality. The difficulty humans have in grasping light's behavior is deeply rooted in the way our minds evolve. Our brains were shaped to survive in a world of solid objects, predictable motions, and direct cause and effect relationships. Tracking a running animal, throwing a spear, or avoiding a cliff all require understanding objects that exist independently and move along continuous paths. These skills reinforced mental models that work brilliantly at human scales, but they are entirely inadequate when applied to quantum phenomena. At the quantum level, the concepts that feel natural, trajectory, definite position, continuous movement, simply do not exist in the same way. Photons and other quantum entities do not carry hidden maps of where they should be. Certain properties, such as position or momentum, only acquire meaning when interactions or measurements occur. Reality at this scale is structured around potentialities, not pre-existing, fully determined states. Our intuition struggles because it demands objects and narratives where none exist. The mismatch between evolved intuition and quantum reality creates persistent confusion. Students often try to imagine what a photon is doing before it is detected or how it chooses a path. These questions feel unavoidable, because they arise naturally from our experience with the macroscopic world, but they do not correspond to anything in the quantum description. Nature does not answer questions we cannot define within its framework, and attempting to force classical reasoning leads only to paradoxes and frustration. Accepting this is uncomfortable but necessary. Understanding does not mean forming a mental picture of familiar objects in motion. It means learning to work with the mathematical and conceptual structure that precisely predicts outcomes. Light is consistent, exact, and governed by rules we can verify experimentally. Our discomfort comes from the limits of our intuition, not from flaws in reality. Recognizing this limitation changes our perspective. It forces us to see that the universe operates according to principles that are fundamentally different from everyday experience. Reality is not obligated to make sense in human terms. It is only obligated to behave consistently. Once we accept this, we begin to think in terms of interactions, possibilities, and probabilities, which is the true language of light and of quantum physics itself. Light challenges our deepest assumptions about what it means for something to exist. In our everyday world, objects have properties whether or not we look at them. A chair is in a room even if no one enters. A ball follows a path even if we do not track it. This is the classical worldview, and it feels undeniable because it is what our senses evolved to interpret. At the quantum level, however, this intuition fails. Light does not possess certain properties independently of interaction. Its position, its momentum, and even the path it takes are not preassigned facts waiting to be discovered. They emerge only through interaction with a measuring device or another system. This has profound implications. The universe at its most fundamental level is not a collection of tiny objects following deterministic paths. It is a network of potentialities constrained by strict rules. The mathematical formalism of quantum mechanics does not describe hidden trajectories or secret classical realities. It describes probabilities of outcomes that are precise, repeatable, and consistent, but not pre-existing in the way a chair exists in a room. When a photon is detected, a definite outcome emerges. Until then, reality is a structured landscape of possibilities, not a predetermined story. Humans struggle with this because our minds crave continuity and causality. We are uncomfortable with the idea that properties can be undefined until interaction. We want a narrative, a what is happening story that our brains can visualize. Light offers no such narrative. It responds exactly as the rules dictate, yet those rules do not map onto any classical picture we can hold in our heads. Accepting this reshapes how we think about reality. It forces a shift from imagining pre-existing objects to understanding relationships and interactions. The universe is not built from classical objects, but from events, probabilities, and interactions. Light is the perfect teacher in this regard. It operates with precise rules, yet it continually reminds us that reality does not need to conform to human intuition. Our role is to learn the language of possibilities and to see nature as it truly behaves, beyond the comforting confines of familiar imagery.